Today we will be deep diving into one of the most critical aspects, how LLM really think to solve complex tasks. We'll be talking about planning phase of an AI system. So in this video, we are going to break down the 5 fundamental strategies that make LLM to think, plan and get the stuff done. We will also see frameworks which are using this approach with some examples as well. And so stay with me till the end. Okay, first is a strategy that let an LLM level up from simple model to a true problem solver. I mean, just think about it for a second. How in the real world would LLM plan a complex task? It's divide and conquer. For a huge complex task, what is the first thing you do? You break it down into smaller pieces, and that's the exact first step a small LLM takes always. Now the fancy term for this is task decomposition. The idea is super simple. Take one enormous goal and just slice it into sequence of smaller bite-sized sub-goals, such that instead of trying to solve the entire at once, it just focus on one little piece at a time. And LLMs can do this in two different ways. On one hand, you have the decomposition first approach, what I also call as master planner, where LLM looks at the big picture and just decompose it. It breaks down into a bunch of smaller sub-goals, and then for each of these little mini goals, it creates a super specific sub-plan to get that one thing done. It's like their golden rule: plan everything first and then execute. It's just pure methodical planning. For example, take Hugging GPT. It's basically like having an AI project manager who coordinates a whole team of specialized AI assistants. Or take an example of Prog Prompt. It turns any task into coding problem by breaking everything down into super specific steps. It's all are having a crystal clear roadmap before taking the first step. Okay, now let's talk about the second personality, which is, you might have guessed it, the improviser. It's the complete opposite. What it does is interleave decomposition. Here the LLM plans one step, does it, see what happens, and then figure out the next move. This is way more flexible and can handle surprises as well. They don't need detailed roadmap, they just dive in and figure things out as they go. Let me show you two incredible examples of this in action. First up, we have got chain of thought, where by adding this little phrase, let's think step by step, to a prompt totally unlocks the LLM ability to reason on the fly. It's not only about having some grand perfect plan, it's about figuring out the very next logical step and then the next one after that. And there is another awesome system called React. It constantly goes back and forth between a thought step and an action step. It thinks, okay, what should I do next? Then it does it, sees what happened and use the new information to figure out its next thought. I have already explained React in detail with its component and live example in the video attached here. So which one is better? Well, like with most things in life, it's a trade-off. The master planner biggest strength is focus, because it builds the whole plan with the end goal in mind. It's way less likely to get distracted or lose sight of the mission. But here is the catch, it's rigid. If an early step fails for any reason, the entire plan can just collapse. But the improviser, on the other hand, is very good at handling errors. If something goes wrong, no big deal, it just rethinks and tries a different next step. It's super flexible, but its weakness is on really long and complicated tasks, it can get lost in middle. You know, after 100 little improvised steps, it might forget what it was originally trying to do. Alright, so breaking down a problem is a fantastic start. But what if there is more than one way to get to the finish line? I mean, a truly intelligent system always considers its alternative option. And we all know that LLM can be uncertain many times. So being reliable is even become more important for it. So how do we make sure that LLM always finds the best possible solution and not just the first thing what comes to mind? And that brings us to our next section, multi-plan approach. This is just like when you use the GPS. It doesn't just give you one route. It shows you multiple and usually highlights the fastest one. LLM agents can do the similar things. they can generate several different plans to reach a goal and then run them through an evaluation process to pick the one that most likely to work. So how do we actually get LLM to do that? First of all, you have got generation. That's where the LLM creates a whole bunch of different plans. Step 2 is selection. That's where a search strategy sifts through all those candidates to find the absolute best one. And you might be wondering, how do you get LLM to generate all these different ideas in the first place? Well, a lot of the time it's done using something called as temperature sampling. That is the inferencing parameter of LLM. It encourages to produce more diverse, more varied output instead of just giving most obvious or boring answer every single time. Okay, so that's just the theory. Now let's jump into specific strategy that are actually using this to put into action. Alright, first framework we'll look at is called as something self-consistency. Imagine you ask a huge crowd of experts for their opinion. That's kind of what this does. LLM generate many different ways to solve a problem and then it just takes a majority vote. Whichever plan pops up, the most often is chosen as the most reliable one. It's as simple as that. But what if you need something a little more organized than just a simple vote? Well, that's where a more structured approach comes in, like tree of thought framework. So instead of a simple list of ideas, the tree of thought framework organizes them into a tree of possibilities. Like branches spreading out from the trunk. To find the best path, it can use two main search strategy. The first is breadth first, which is like checking all the branches at one level before you move on any deeper. The other is depth first, which is like following one single branch all the way to the end to see where it goes before you backtrack and try another. It's a way more systematic method of exploring all the ideas. And believe me, this idea is evolving very fast. Now, this all sounds incredibly powerful, and trust me, it is. But there is always a catch. So let's talk about the trade-offs. First is computational demand. Generating just a single plan is cheap and faster, but generating and evaluating tons of different plans, that's a huge jump in computational cost. And second, you have evaluation reliability. A lot of the time, you are asking LLM itself to basically grade its own homework. So you really have to trust its own judgment. And finally, there is stochastic or random nature of it all. There's temperature sampling, which causes very randomness that fuels the creativity that sometimes lead to inconsistent results also. At the end of the day, the key advantage here is scalability. When problems get crazy complex with this huge space of possible solution, this brainstorming ability lets an LLM explore that space way more broadly and effectively than any one-shot approach ever could. So LLM is a great generalist, but sometimes you need a specialist or problems with really strict rules, like think about robotics, where one wrong move could have a physical consequences, or super complex math problem where you cannot simply guess. So what do you do about that? Well, the answer is you don't try to fix the LLM. Instead, you give it a partner. It is all about letting the LLM recognizing when a problem needs a dedicated tool. And the most important word there is integrating. This is not only about replacing the LLM. In this new setup, the LLM job totally changes. It takes on the really interesting support role, where instead of trying to figure out the whole puzzle on its own, it uses its number one skill, that is language, to basically become a translator. It takes a messy, complex problem and formats it perfectly so its specialist partner can step in and solve it. So how LLM do this? It's a two-step process. Step 1 is task formalization. The LLM does its own thing. It reads the problem, understands on the language and translates it to a perfectly structured format. Then it makes the handoff. That's step 2, external planning. The specialist planner takes that perfect blueprint and builds the final plan, one that is guaranteed to work within the rules. It's a perfect division of labor. You can draw an analogy to function calling or tool calling with it. But who are the specialist partner exactly? Well, it turns out that there are a couple of different types. So on one side, you have symbolic planner. These are our logicians. They are all about formal rules, logic, and doing things 100% by the book. But symbolic planner always had one huge problem. Setting them up used to be this crazy complex process that only human experts could do. Look at the first framework using the symbolic planner LLM plus P, where the LLM translates the problem into a specialized language, which is called as PDDL. Think of it as a universal language just for planning problems. And it's a similar idea with LLM plus ASP as well, just with a different specialized language. On the other side, you got the neural planner. Think of them as deep learning models that have trained in one specific area. But if you take them out of your comfort zone with a new type of problem, they will really struggle. And that's exactly where the LLM comes in, giving them the broader context and flexibility they need to handle anything new. The fantastic example of this framework is called CAM, where the LLM acts as a brainstormer and it comes with a whole list of possible moves or actions. Then the neural planner, that is the expert, steps in. It looks over the list and uses the deep training to pick the absolute best option. The most fascinating framework of all is one called as Swift says. It's actually built on a famous idea of psychology called dual process theory, which says we have two different ways of thinking. It uses a super efficient neural planner for fast thinking that make all the quick, intuitive kind of decisions. While that model does most of the heavy lifting, but when it hits a wall or runs into an error, it cannot solve. It calls for backup. And that's when the LLM with its powerful slow thinking ability is brought in to do the deep, careful, complex reasoning that need to figure out the problem and gets things back on track. LLM often suffers from hallucination issues and inefficient reasoning capability when tackling complex problems. This can lead to the agent making errors or getting stuck in thought loops due to limited feedback. To solve this, we turn into our new fourth core methodology, that is reflection and refinement. It's not just about making a plan, it's about what you do when that plan fails. It's about learning from failure. This strategy gives LLM the ability to look at a failed attempt, figure out what went wrong, and then come up with a better plan for the next try. This creates this really a powerful feedback loop. The feedback it gets is not just a number, it is text. The LLM generates its own critique in a plain text. That's essentially telling itself, okay, that didn't work because of this reason. So next time I should probably try that instead. It's like learning through self-talking. And the real goal here is not just about getting the right answer in the end. It's all about improving what's called as fault tolerance. Basically, the AI's ability to handle its own screw up without the whole system getting crashed down. Well, you can pretty much break it down into simple repeating three-step cycle. So first, the LLM creates an initial plan. That's its best first shot at solving the problem. But if that plan fails, and it probably will, it moves to the second step, that is reflection. This is where it criticizes itself, figures out the root cause of the failure, and finally in step 3, what it does is the refinement. It takes that critique and uses it to craft a new smarter plan. And this little loop just keeps going until it nails it. There are several big frameworks out already putting this idea into practice. For instance, a framework called reflection that gives the LLM as an internal evaluator. It has its own critique which actually use outside tool like search engine to fact check its own work. And then there is Lemma, which is a huge powerful LLM to act as a teacher and for a student AI, creating a new training example along the way. Along with reflection, I have explained 6 different agent architecture in the video attached here. This whole idea of learning from feedback sounds like a lot like reinforcement learning, but there is a key difference in how these LLMs are learning from reinforcement learning. In traditional reinforcement learning, feedback is super simple. It's just a number like reward or penalty. But with LLM self-reflection, the feedback is rich self-generated text. The LLM is literally talking to itself, writing a detailed critique that says what it does next. For all its promise, this whole approach has one major critical limitation. Unlike a math algorithm where you can prove it, it will eventually find the right answer. This process comes with no such guarantee. There is no mathematical proof that an LLM reflecting on its own mistake will always lead to success. That brings us perfectly to our final method. Learning from your last mistake is very powerful for sure, but what about learning from all your past experience? For human, this is called memory. Similarly, for LLM that's trying to tackle a complex multi-step goal is not just relying on its immediate instruction. It needs context. It has to remember what it has worked before, what failed, and what it learned from all its previous steps to plan effectively. Without it, like planning everything from scratch with zero past experience, it's just not very efficient. This powerful concept called memory-augmented planning. We give the LLM an external memory, a place where it can store past success, past failure, useful fact, and all the context from previous job. So the key difference to understand here is short-term versus long-term memory. The LLM long context window, that it's short-term memory where it can think about right now or present, but hooking up it to an external database gives it a long-term memory. So how do we actually build this memory? The first is what we call as RAG. Yes, retrieval augmented generation. This is my absolute favorite way to explain RAG. And you can think of it like an external library. The LLM can look up to the past notes and documents whenever it needs to. It's really easy and cheap way to give the real-time external information. But their success relies on the accuracy of the underlying retrieval algorithm. Frameworks like generative agent just store memories as plain text, while memory bank kind of frameworks get a little more technical and turn this experience into mathematical vectors so they can find memories that are conceptually similar. Then you have got the remember framework, which even keeps tracks of good and bad memories as well. Before moving advanced, let's just double click on the MemGPT framework, because the analogy they use is just perfect. It treats LLM context window like a computer's RAM. You know it's super fast but limited. The external memory source, on the other hand, is like computer's massive hard drive. It's slower but hold way more stuff. The other way is more like developing muscle memory. This method is called as embedded memory, and it doesn't use any external library at all. Instead, it takes past experience and use them to retrain or fine-tune the LLM itself. This gives it a massive capacity to remember things instinctively. We are seeing this practice with frameworks like CAM or agent tuning. But operating that memory is really expensive because it means you have to retrain the whole system. That's why engineers use this really clever technique called as PEFT, parameter efficiency fine tuning. These methods let them update just a tiny fraction of model's parameter, which makes it way cheaper and faster to bake into these new memories. So which one is actually better? Well, as this table shows, there is really a clear trade-off. RAG is fantastic for saying current, but for example, customer service bot that needs absolute latest product information. But if it cannot find the right memory, it's pretty much useless. On the other hand, fine-tuning gives LLM a deep, intuitive grasp of patterns, which is perfect for learning a stable skill, but like how to play a game. But here, updating that intuition is expensive, and sometimes it can lose a specific little detail in the process also. For both of these methods, there is one persistent fundamental challenge. The memories this system creates, whether they are stored inside or outside, are often generated by LLM itself, that reflects on its own experience. But if a weaker LLM is not very good at understanding what it's doing or drawing the right conclusion, the memories it creates for itself is not going to be very good either. A truly intelligent AI system always look at a problem and dynamically switch between all these 5 strategies, picking out the absolute perfect tool for the job at exactly the right moment. So that was a little peek inside how an LLM really thinks and plans. If you enjoyed the video, hit the like button, share with others, and definitely subscribe for more such videos that break down the world of AI. Till then, keep learning, keep coding, and keep growing.